All right, for the last couple of days, we've talked about concavity. We talked about it with polynomials and with radicals and rationals. And now what we're going to do is talk about that point of inflection. Now we're going to say, is there a point of inflection? And what a point of inflection is a point in which the concavity changes. But we have to be careful because it has to be a point. It's not always going to be a point where we have a change in concavity. We could have a change in concavity about an asymptote. So that's really what we're going to be focusing on today. What are those points of inflection? So let's go ahead and talk about finding those points of inflection. The first thing we're going to do is examine the concavity of our function. And to examine our concavity of our function, we're going to be looking at the second derivative. And we're going to be setting it equal to 0. So the first thing we're going to do is go ahead and find our first derivative, f prime of x. We get 3x squared minus 6. Second derivative gives us 6x. In this case, we're going to go ahead and set that equal to 0. If I set that equal to 0, I end up with x equal to 0. So I'm going to go ahead and do my intervals. I'm going to go from negative infinity to 0 and 0 to infinity. So this is not going to look anything different than we have done the last couple of days with our concavity. We're going to find our test values. So I can test negative 1, I can test 1. I'm looking at the sign of the second derivative. So if I take negative 1 and plug it in there, I get a negative value. If I plug in 1 to my second derivative, I get a positive value. So I see that I have a concave down and a concave up. Again, nothing new at this point. Now what I'm interested in, though, is where this changes. Do I have a point of inflection? Or is it something else that's happening? So right now we're going to call this a possible point of inflection. We have a possible point of inflection when x equals 0. So we'll say possible POI. We abbreviate it as POI. It's understood to be point of inflection. So what does it have to be? What has to happen for it to be a point of inflection? Well, we have to be able to plug x equals 0 in to the original function to get a y value out in order for it to be a point of inflection. So I'm going to find f of 0. So if I find f of 0, I end up with 0 minus 6, which gives me, 0 minus 0, which is 0. So I do get a point at 0, 0. So my possible point of inflection is now a point of inflection. So I have a POI at 0, 0. So ultimately, we're not really doing a whole lot of new material today. We're just now classifying, is this an actual point of inflection? So we're taking it one step farther than we have for the last couple of days. So what I want to do is go ahead and look at a couple of polynomials and then maybe look at a rational and a radical if we have a little bit of time here. So again, we're going to find our first derivative. So we get 6x squared minus 6x plus 18. Go ahead and find the second derivative. We get 12x minus 6. We're going to set that equal to 0. If I set that equal to 0, I get x equal to 1/2. So my intervals, we're going from negative infinity to 1/2, and then 1/2 to infinity. I can go ahead and find some test values. We'll change a marker here. Kind of running out of ink there. So I'm going to test negative infinity to 1/2. I can plug in 0. 1/2 to infinity, I can plug in 1. I'm looking for the sign of the second derivative. So if I plug in 0, I get 0 minus 6, which is the negative. 12 minus 6 is a positive, so I'm concave down and then concave up. So again, I have a possible point of inflection at 1/2. What I'm going to do is go ahead and plug that in to my original function to see if I get a value out. So I'm looking at f of 1/2 gives me 2. 1/2 to the third gives me 1/8. Minus 3 times 1/2 squared gives me 1/4. Plus 18 times 1/2. Sorry, I wasn't paying attention to what I was doing. Minus 7. So here I get 1/4 minus 3/4 plus 9 minus 7. We've got negative 1/2. And then here we get 2, so we get 3/2. So we do get a point. So 1/2, 3/2 is a point of inflection. Now this one here, this next one, we're going to see something maybe a little different happen, possibly. Let's see what happens here. Second derivative. Well, we first find our first derivative, 4x to the third minus 6x squared. And then our second derivative gives us 12x squared minus 12x. Go ahead and set that equal to 0. So we get 12x times x minus 1. So we're going to see we're at 2 points here, don't we? We get x equals 0 and x equals 1. So what's going to happen here? Well, let's go ahead and plug in or find our intervals. We have negative infinity to 0, and then 0 to 1, and again 1 to infinity. I want to go ahead and test negative 1, 1/2, and 2. So we can go ahead and find the sign of the second derivative. The sign of the second derivative, negative 1. And we're going to plug in this negative in this factored form. Plugging in negative 1, I get a negative times a negative, which is a positive. Plug in 1/2, I get a positive, and then here I get a negative, so I get a negative, and then 2, I get a positive and a positive, which is a positive. So I have concave up, concave down, and then a concave up. So I have three intervals there. I have 2 possible points of inflection. I have one at possibly at 0 something, and then one at 1 something. Again, that's happening at those x values in between there. So what's happening there? Well, if I plug in 0, do I get something out? 0 minus 0 is 0, plus 6 gives me 6. And if I plug in 1, I get 1 minus 2 is negative 1, plus 6 gives me 5, doesn't it? So I get 2 points of inflection for this problem. So we could see that we have many more than just one point of inflection. All right, last 2 examples here. I have a radical and I have a rational. So let's go ahead and talk about the 5th root of x, or which is equal to x to the 1/5. So if I look at x to the 1/5, I'm going to go ahead and find my second derivative. First thing I'm going to do is find my first derivative. So we get 1/5 x to the negative 4/5. And I'm not going to take this to the denominator just yet. I'm going to go ahead and find that second derivative. Second derivative, I get negative 4/25 x to the negative 9/5. Again, multiply your exponent to the coefficient. 1/5 times negative 4/5 gives us negative 4/25. And then negative 4/5 minus 1 gives us negative 9/5. Now I can go ahead and take that to our denominator. We get negative 4 over 25x to the 9/5. I'm going to go ahead and set that equal to 0. We'll run out of room there. But remember, again, we're going to take the numerator equal to 0. And we're going to take the denominator, set it equal to 0 as well. Negative 4 equals 0. That doesn't make sense. We get rid of it. 25x to the 9/5. Divide your 25 over, so we get x to the 9/5 equals 0. And at x to the 9/5, we can take the 5/9 power to both sides, and we end up with x equal to 0. So what we're going to see is our intervals being from negative infinity to 0 and 0 to infinity. I can test negative 1 and I can test 1. And I'm looking for the sign of the second derivative. So my sign. So what do we get? Well, if I plug in negative 1 in, again, that negative 4, that's always going to be negative, isn't it? So I have a negative divided by something. Well, what is that something on the bottom? If I take negative 1 and plug it in for x, negative 1 to the 9/5 power, what does that mean to me? Well, if I think about that, I can write this as the 5th root of negative 1 to the 9th. Negative 1 to the 9th, a negative to the 9th is going to be a negative value. So I get the 5th root of negative 1. The 5th root of negative 1, since I'm taking an odd index of a negative number, I can get a negative number out. I get -1. So that's going to give me a negative value, which will end up being positive. If I take a 1 and plug it in, that's going to be a positive on the bottom. So I get a positive there, and a negative divided by a positive gives me a negative. So I have concave up, and I have concave down. Well, what's going to happen? Do I have a point of inflection? Does it exist? Does this value exist? So I have my 0. That's the value I'm looking at in between these two intervals. If I plug 0 into the original function, the fifth root of 0 is 0. So I have a point of inflection at that point as well. Last but not least, we have our rational. Again, we're going to find our second derivative. So we're going to start with our first derivative. And we have a quotient rule. So I have low d high less high d low. Draw the line. Denominator squared we go. I'm going to go ahead and clean this up. We get 2x plus 2. This looks like it's going to work out fairly nicely for us, isn't it? 2x are going to cancel. So I'm left with 2 over x plus 1 squared. Since we have just a nice constant on the top, I can go ahead and bring that denominator to the numerator. So I have a chain rule. So my second derivative in this case is going to be -4 times x plus 1 to the -3rd times 1, or -4 over x plus 1 to the 3rd. Again, we're going to set that equal to 0. Setting my numerator equal to 0. At this point, I'm going to guess that most of us see that there's no variables up there, so we don't have to worry about it. The only value that we're going to get is when it's undefined, or when x plus 1 to the 3rd equals 0, or x plus 1 equals 0, or x equals -1. So my intervals, running out of room, I'm going from -infinity to -1, and -1 to infinity. I'm going to go ahead and test. I'm going to test -2, and I'm going to test 0. Again, I'm looking at the sign of the second derivative. So if I plug in -2, again, that top always going to be negative, isn't it? So I'm going to go ahead and put that into my chart. If I plug in -2 to the bottom, I get a -2 plus 1 is a negative. To an odd exponent is going to be negative. So that gives me positive. And if I plug in 0, 0 plus 1 gives me a positive. To the 3rd is going to be positive. So I get a negative. So I get concave up, and I get concave down. So again, I have a possible point of inflection at -1. So what I got to do is take that -1 and plug it back in to my original to make sure I get a point. If I plug in -1, 2 times -1 gives me -2 over -1 plus 1. Uh-oh, that's 0. -2 is not divisible by 0, is it? So we know that f of -1 does not exist. So this point of inflection does not exist. So for this problem, there is no point of inflection. Well, maybe if we go back to the original problem, the original function, that maybe makes sense to us. What happens when x equals -1? When x equals -1, we have, yes, an asymptote. So we have to be very careful to make sure that these changes in concavity occur over a point to get a point of inflection. Otherwise, there is no point of inflection at that point, or at that value. So a couple of things that we saw today were the polynomials, the radicals, and the rationals, and finding those points of inflection. Good luck, enjoy. If you have questions, reach out and give me a question or two. Good luck.